healthy and doesn't need the drug as someone who actually needs the drug, and this can actually really damage them, right? So there's lots of situations where you might want to use precision instead of overall accuracy. Okay, now there's another thing here, another one. It's called recall, another metric. Okay, and this one is out of all the actual like positives, how many did the model detect? So this is a little bit different. You can see that the formula is the true positives over the true positives plus the false negatives, right? Before, for precision, it was the true positives plus the false positives. But here, it's the true positive plus the false negatives, right? And what is this denominator here? The true positives plus the false negatives. It's the total amount of people who are like the positive label, right? Because you have the true positives and the false negatives. So in our example, right, we predicted that 18 were sick when they were actually sick. The true positives were 18. But we incorrectly predicted that 2 are healthy when they were actually sick, right? So the total number of sick people, the positive labels here, I know it's kind of confusing because we say sick as positive label. That's like the wrong connotation for the word sick, but positive label just means like the thing the model wants to predict. Okay, so the total number of positive labels here is 20. Okay, the total number of sick people, and our model correctly got 18 of them. So we have actually a pretty good, I guess, a decent recall of 90, right? 0.990% recall. Okay. And you can see that this is like the same set of predictions, right? The same model, but you have different numbers for each of the measures. So you have like 0.78 for the precision, you have 0.9 for the recall, right? And once again, this is where you're sort of, you would use this in a certain situation, perhaps one different from using a precision, right? You want to, let's say you're, diagnosing sick patients, right? In the medical field, okay? In this case, having a false negative is extremely detrimental, right? It's very bad. Like if you're trying to diagnose someone with a serious illness, okay, a model's trying to diagnose someone with a serious illness, and a model misses that, right? A false negative, right? They're actually sick, but the model predicts them to be healthy. That's extremely terrible, right? Because the sickness goes unchecked. So in a medical setting, perhaps recall will be more important than accuracy. Okay, I hope you guys are sort of understanding that in each of these situations, each of these metrics, right? There is a situation that might be more suitable for that particular metric. And there's also another one called specificity, right? So out of the actual negatives, so how many did the model detect, right? So the specificity is the true negatives over the true negatives plus the false positives, okay? So in our example, right, we correctly predicted that 75 were healthy and they were actually healthy. So those are the true negatives. But we incorrectly predicted that 5 were sick or positive when they were actually healthy. So those are the false positives. Okay. So you can see here that the specificity is 75 over 80 is 0.94. Okay, so a pretty high specificity. And once again, right, you have to think about situations where you might want to use this over, say, recall or this thing before, right? Once again, I bring up the example of the spam email, right? You really don't want false positives for spam detection, right? Because you can miss important emails and everything. So when you're training a model for that, perhaps you might want to care about the specificity a bit more. But notice how like all of these metrics pop out from the confusion matrix, right? So if I give you a confusion matrix for a model, right, you should be able to sort of calculate all of these metrics depending on what you want. Okay, so now, here is something that is also very interesting. It's called the receiver operating characteristic. It's called the ROC curve. So the ROC curve tells you the performance of a classifier by plotting the true positive rate, okay, sensitivity against the false positive rate. Okay. So it basically tells you how well the model separates positive versus negative classes. Okay. And for the ROC curve, right, you would ideally want a curve that is up and to the left-hand corner, right? So if your curve is like a sort of right angle, right? If it goes like this and this, then it would be perfect, right? But you know, in very few cases models are like that. If the curve is just a straight diagonal line, then it's like a random classifier, okay? But if you sort of if it's going up towards the top left corner, it's a better and better sort of classifier, okay? And this is sort of seen from the AUC metric, the area under the curve, right? If the area under the curve is 1, okay, then you have a perfect classifier because you can see that the area of this sort of grid, this box is 1, right? It's 1 by 1. If the area is 0.5, then it's bad, right? Because it's like this triangle down here. And you want the AUC to be as high as possible, right? Because as you get to the top left corner, the area under the curve increases more and more and more. Okay. And I hope that, you know, everybody can sort of see why the ROC curve is the way it is, right? Because you ideally, this point here, you ideally would want a 0% false positive rate and a 1% true positive rate, right? Up here, this point here. But most of the time you'll get a curve that is, you know, not quite at the top left corner. But you ideally you would want sort of your like true positive rate, right, to be sort of always higher than your false positive rate, right, to sort of be up here, right? I hope people sort of see why you want it to be up here. Now there's another one, right? It's called the precision recall curve. So this one sort of like plots precision versus recall. Okay. It sort of tells you how well the model like identifies the positive class, because recall that both precision and recall deal with true positives, right? You care about how well the model predicts a positive class, right? So this curve like plots precision against recall, right? So if you have a point up here, it means you have high precision, right, and low recall, okay? And down here you have high recall, low precision. And this is sort of like you kind of want like a trade-off here, right? You want to it tells you a trade-off between like sort of catching more positives, right? Because precision is catching like more positives. Wait, no, sorry. Recall, I think, would be catching more positives. Okay. And no, sorry. Okay. Precision is catching more positives, and recall is avoiding false alarms. Okay. So, you know, your model might be somewhere around here, but this is like a trade-off curve that can tell you where your model is sitting. Is if it's better at, you know, predicting predicting positives, or is it better at avoiding false alarms? And finally, there's something called the F1 score. Okay. Also, by the way, let me just say this. These things are like these curves are sort of, at least from what I can see in my experience, reading papers and doing research, they're more sort of prevalent in like the medical field. Like if you go into like AI plus medicine, that you see these curves more. But yeah, just letting you know that. But this one is more general. So F1 score combines precision and recall into one metric. Okay. It sort of tells you how well the model balances correctly finding positives with being accurate when it predicts positives, right? So F1 score is this thing here. right? It's a pretty good metric when you care about false positives and false negatives, right? Because you can see precision and recall both involve them. Okay. And it's helpful in class imbalances. But the limitations is that it sort of ignores like the true negatives. Like if you care about that, the true negatives and the specificity, right? So, I mean, I've just presented like a bunch of metrics here, right? The idea is not for you to sort of memorize their formulas or anything like that, or these curves or anything, but to just like give you an idea of like when you should use what metric, right? Because they're not all equally useful in every situation. Recall the medical example and the spam email example I gave earlier, right? Depending on your use case, you probably want to prioritize a certain metric over them. Okay, before I move on to bias variance, is there anything or any questions? It's okay, I'll finish this. No? Okay, perfect. So this is a very important concept, bias and variance. Okay. Bias is sort of how accurate an estimate is to the true value, right? Models with high bias are often oversimplified and pay little attention to the training data. So let's say this example here, right? Let's say you're trying to fit a curve to these points, okay? These sort of this set of points here. You can see that this particular model, a linear or yeah, like a straight line constant model, is terrible, right? It barely fits the points at all, okay? And it's a not very accurate estimate of the set of points. So this model, this sort of straight line model has high bias. It's very inaccurate, okay? And this is something we call underfitting your data, meaning that you don't sort of take into account your data enough. So your model is very bad. Variance is how sensitive a model is to fluctuations in the training data, sort of how complex the model is, right? Models with high variance are too complex and unable to generalize to unseen data. Okay, what do I mean by that? So on the other side of the spectrum, you have variance. You can see here that this model, right, fits the points perfectly, okay? But notice how complex this model is. It's like a, yeah, I don't even know what this like function is. It's like a very jagged, overly complex fitting. Now, why is this bad, right? Why is this bad? Let's say you have another point, right? Right here, okay? There's a point right here where my cursor is. I hope you can see, right? This model with high variance will not be able to generalize to that point, right? It will not be able to sort of it will not be able to sort of account for that point because it's fit too tightly to these points, right? But you can see that this point here might belong to, you know, these set of points, right? It's like kind of in the curve, right? But this model with high variance won't be able to generalize to this. Similarly, let's say you have a point like here as well, right? Your model, this sort of very high variance model, won't be able to generalize to this data point. However, and see is what I mean, right? You don't want a too complex model that overfits, right? This is called overfitting, that overfits on your training data. So what would you want instead, right? A good balance is something like this, right? You want to capture the general sort of trend of the training data, the distribution of the training data, but also leaving it sort of room for generalization, right? So for these set of points, you could, I mean, you guys could probably have seen, eyeballed it and seen that it's some sort of maybe quadratic function, right? Some parabola. And you can see that this curve has low bias because it fits the curve or it fits the points well, right? It's not just a straight line. And it has low variance. It's not too complex. It captures the pattern of the points without being, you know, doing too much, right? It's not like the one before where you're like trying to, you know, zigzag and fit everything, right? And here you'll have a low training error, low bias, but also you can generalize to points, right? If you have like a point here, right, you can see that it sort of, fits on this parabola as well. So ideally, this is what you would want in a model. Okay. So what is the bias variance trade-off? Okay. It's a conflict between a model's complexity and its ability to generalize to new unseen data. Right? Because if you look at the definition of bias and variance, you'll notice that they're sort of opposites of each other. It's an oxymoron, kind of, right? Because models with high bias are oversimplified, whereas models with high variance are too complex. You can see that bias and variance sort of like they pull each other in opposite directions, right? So this is why there's a trade-off here, right? As you increase model complexity by reducing the bias, right? Because the bias is a model that's too simple, right? As you're increasing the complexity and you're reducing the bias, you increase its variance, right? Because you might risk the model becoming too complex. However, if you increase if you simplify the model by reducing the variance and like making the model less complex, okay, you increase bias. So this is kind of like a trade-off here. And if you see this graph, so actually you can, I think, you can mathematically prove, I believe, don't quote me on this, that the total error of your model or how wrong your model is, your total model error can be decomposed, like it's equal to the sum of the variance plus the square of the bias. Okay, so you can see that in this curve here, right? If you have a model with high variance, okay, you have a model with low bias, and your total error will be up here, right? Ideally, you would want something sort of down here, okay, where the bias and variance are sort of kind of low, but not as low as they can be, right? You can see that this is the optimal point, right, with the lowest model error, and the variance here isn't the lowest it can be, and the bias here isn't the lowest it can be. They're both a little bit higher than the lowest it can be, but that actually is the point that corresponds to the lowest model error, right? The idea here is that you can't sort of put all your eggs into the variance basket or put all your eggs into the bias basket because there's trade-off, right? If you increase one, you'll decrease the other. So you have to find a balance, okay? And that balance is where your model actually performs the best, a balance between model complexity and its ability to generalize. Okay, I hope it's clear what the bias variance trade-off is. So what are ways for reducing both or balancing both, right? To reduce bias, you can train for longer, right? If you have a model, okay, let's say, I think you guys know what neural networks are. Let's say you have like 2-layer neural network for classification, right? Initially, your model is terrible, right? High bias, the model error is very high. But if you train it on this data for a long time, the model will get better and better and better, right? Because you'll see the data more times, and then you'll have lower bias, right? Or you can make a more powerful model, right? As I've said before, bias arises when a model is not as complex, right? Doesn't have as much expressive capability to capture the patterns in the data. So instead of a 2-layer neural network, you can make it a 4-layer, a 10-layer neural network, right? Or you can increase the hidden size of the neural network from, let's say, 2 to 4 or to 8 to 16. You can increase how large a model is, the number of parameters in the model, and this will help you reduce bias, right? It's more powerful now, okay? But notice, if you increase the size of the model, you make the model more complex, and now you'll increase your variance. So what are some ways of reducing variance? There's something called regularization, okay, which is sort of reducing the model's capability to be overly complex without actually reducing the size of the model itself. Okay, so let's say you really want to train a 10-layer neural network, okay, to reduce your bias. but now your model's overfitting, right? Your model's like sort of having high variance. And you want to reduce this variance without actually shrinking your neural network back to like a size of 2 or 3. So what are some techniques you can use to do that? Okay. Because one way of definitely reducing variance is by reducing the size of your model, right? But ideally, you don't want to do that because a bigger model means a more powerful model. So one thing you can do is rather than reducing the size of your model is doing L2 regularization. Okay. This is a thing that basically penalizes the model for how large its weights are. Okay. So usually this takes the form like in the loss function, you'll add a term that is the square of the magnitude of your weights, right? So if your model has very large parameters, like very large numbers for its parameters, the L2 error is going to be high. Okay. The L2 regularization term will be high. So this will force the model to decrease its magnitude, its parameter magnitude. And why does this help? Because if your model has very high numbers for its parameters, for its weights, okay, then it's in a sense, right? In a sense, overfitting, right? It's being too confident, right? If its weights are large, it's very confident in something. Maybe it's fit the pattern too well and it's too confident. So if you reduce the size of the weights, it can prevent the model from becoming overly confident. Okay. So that's L2 regularization. Dropout. Okay. This is removing random parts of the model during training. Okay, it's a very naive. You could argue it's very naive, but it works very well. Okay. Like while you're training the model, you literally like take some parts of the model and just remove them. You zero them out. Okay, the weights zero, you zero out the weights, right? And this reduces model complexity. Why? Because you literally have a smaller model, right? You're like zeroing out weights during training, right? But you're not reducing the size of the model. So what would happen is like you're training, right? And every iteration you train, you zero out random parts of the model. You don't always zero out like a specific section of the model. You zero out like random places. Okay. So this ensures that every part of the model sees the data, but don't see the data too much to overfit. Okay. I hope that kind of makes sense. Another one is early stopping. And this is literally like, you know, as the name suggests. Okay. If you train for too long, right? If you train a model for too long, right? The model might fit the data too well, right? This might happen, right? It fits the data too well, meaning it goes through all the data points, right? Recall, right? The model with the best balance doesn't really go through all of the data points, but captures the general pattern. But if you train for too long, the model might learn to just trace through all of the model data points to drive the error to zero. So early stopping just says, okay, I'm going to train until the model's kind of good enough and just stop it there. Or literally like, literally hitting the stop button, right, in VS Code or something. You stop the train. And it works, it prevents the model from overfitting. I hope that's clear what regularization is. Yeah. Now we're going to talk about data augmentation, which is another way of reducing variance and I guess bias as well. But it's a very powerful thing that you can do, especially in image tasks, like when you're working with images. And this is more of a setup for like next week when I'll talk about convolutional neural networks. So let's assume that you're training a model to classify cats and dogs, right? When you give the model an image, you want the model to say like, okay, this is a cat, okay, if it's a cat, and this is a dog if it's a dog, right? And let's say you have various images of cats and dogs, okay, like the ones here. But let's say there are two situations. Let's discuss two situations. The first situation is a lack of data. So let's say you only have these two images of cats and dogs, right? Will you be able to train a good model with only two images? No, right? You only have two images. The second situation is sort of this one. So let's say you do have enough data to train a good model, okay? But the images you have, right, the data you have are like these ones, okay, are all very similar to this one, right? You have a cat and a dog who are like sort of, upright, um, in the middle of the image, right? Maybe the background is white, okay? And the orientation is all good and the zoom is all good. You can see all of the cat and all of the dog. Okay, let's say all your data is like this. Let's say you have like 10,000 data like this. So you do have enough data. And you train the model on that. However, now, right, the model is given this image of a cat. Okay. And this is very realistic because in the real world, right, if you're like designing a product for customers, okay, you can't really expect customers to take images perfectly, right? I mean, how many times you just whip out your phone and snap an image, right? The image might be blurry. It might be upside down like this. It might not have the entire cat in the picture, right? Because look, this cat doesn't have its whole body in the picture. And the background could be anything, right? You can see this cat has a green background. So will your model be able to classify this image? Maybe, right? Maybe, right? Because I mean, if the model is good enough and it learns the features of a cat, like the ears, the eyes, the fur, maybe, it can still maybe classify this image. But ideally, you would want a more surefire guarantee, right? It might not be able to, right? It might not be. It may or may not be able to do this image, classify this image as a cat. So, but you want it to be more robust to these sort of weird images. So what do you do? Okay, you do data augmentation. Okay, data augmentation is the process of artificially increasing the size and diversity, okay, of a training data set by applying label preserving transformations to existing examples. Okay. So given a cat image, right? If you rotate the image, it's still a cat, right? If you flip the image horizontally, it's still a cat. If you flip it upside down, it's still a cat, right? This is still a cat, whether it's right side up or upside down. If you add noise to the image, like if you just inject a bunch of Gaussian noise to the image, it's still a cat, right? But what if you crop the cat out of the image? It's not a cat anymore, right? Or let's say you just, I don't know, you uh like for data augmentation, you're like you just put an image of a horse in there or something. That's not a cat or a dog, right? So you must modify your data, but in a way that's label preserving. Okay, you can't just do anything to it. And for a more practical example, right? When I was at my like internship, for example, we had to do something called depth detection, right? You train a model to detect the depth of something. And depth works by taking in two images, okay, a left image and a right image, okay, and comparing the pixels on the same like row in the left and right image. Okay, that's kind of like how our eyes detect depth, right? It's like the disparity, it's like difference when you close one eye versus the other. So we had to do data augmentation, right? Now let me ask you, if we're trying to like do that, right? If we're trying to make the image, right, compare pixels on the same row in the left and right image, which augmentation we can't do, right? We can add noise, right? The pixels are still there, okay? But we can't rotate the image. Why is that, right? If you rotate the images, this pixel, like, and let's say it's a random rotation, right? This will mess up the alignment of the pixels on the same row. So it no longer works. Does everyone see how the transformations must be label preserving? So here we go. Here are some examples of data augmentation, okay? If you have the original image here, right? You can flip it, you can rotate it, you can blur it, you can increase the exposure on the image, you can increase the contrast on the image, you can make the image grayscale, or if you have this image, you can zoom in, you can zoom in, to its head, to its body. You can zoom out. You can zoom into its like feet, or you can like crop, right? You can crop out part of it, right? Part of the dog's, face, body, tail, neck, etc. Okay. But notice that these are all valid sort of augmentations. You're not changing the image in a way that the model can no longer tell if it's a cat or a dog. I gave the example of cropping earlier, but that's like if you crop out all of the dog, right? That would be useless. You can crop, but you might want to crop out like, you know, parts of the dog instead. Okay. So, I mean, you can see that there really is like unlimited amounts of augmentations you can do, right? So given the two situations above, okay, I said there was a situation where you lacked for data. You didn't have enough data, right? You only had these two images. So what can you do to increase your data, right? Ideally, you want to find more images of cats and dogs, different cats, different dogs, okay? Because that is always the best option, just more data of cats and dogs. But if you can't do that for some reason, then one way you can resolve this is if you just do data augmentation. You take the image, the one image of the cat you have, flip it, rotate it, increase exposure, zoom in, zoom out, right? This isn't this is the same cat, right? The same cat image. But by doing these augmentations, you're teaching the model more about the cat, different features of the cat. You can do the same with the dog, right? For the second situation where I was saying, okay, will the model be able to predict a cat that is like this if you only had data points that were like this, right? You can see how data augmentation might help with that, right? If you take these cat images, right, and you apply a flip, you zoom in, you zoom out, right? A lot of different cat images like this. You can see that it will eventually maybe capture an upside down cat that is not completely in frame, right? So your model will become more robust and more reliable on these other sort of weirder images. So data augmentation truly is powerful. And another application are like class imbalances, right? Let's say you have 5 images of dogs and 1,000 images of cats, right? Without any data augmentation, if you just train a model on this, right? Your model will just always predict cat no matter what image it gets, because on the training data, it will have a training accuracy of what? 995 out of 1,000. That's pretty high, right? 99.5% training accuracy. Am I right in that? Yeah, I think so, right? But you don't want that, right? Because you want it to predict the dog images as well. So what you can do is you take the 5 dog images and you generate 1,000 other dog images by just doing transformations to these 5 dog images. Okay. So now you'll have 1,000 dog images and 1,000 cat images. And now the model will be more balanced. Once again, I have to stress, okay, it's not as good as actually getting out there and getting more dog images, right? Because, transformations will only take you so far. But, it's better than nothing. So, crucially, this reduces overfitting, right? Because if you think about it, if you have or reduces the variance, why does this do that? Because if you have a lot of diverse data, right? Harder data points, right? A rotated cat, zoomed in cat, blurred cat, the model is less likely to learn this data as well as it can, right? The model's job is harder, okay? So therefore, this will reduce overfitting, right? Because the model is less likely to fit itself very well to that data. Okay, that's it for the slides. Yeah, if you have any questions about what I just asked or what I just presented, please ask. And I think now we'll do something.
So we're gonna take a maybe a quick 10-minute break. And then we do have a notebook that's gonna for later that's gonna be going into just kind of evaluating different models and such. it is going to be going into a little bit more of complex topics like what's it called? Convolutional neural networks, which I think is a topic for next week, but it's like going to be a quick intro to that. Yeah, so we're just going to go for a quick break right now. Yeah. Wait, how do I minimize this? Okay, hi guys, we're gonna be back and we're gonna be going over a notebook, which I this week we're going to be doing in Colab, so Google Colab, because like we do need access to a GPU and such. So if you go into the Discord channel, I did share two files. One is a utils.py file, and another is the questions which we're going to be going into. So essentially, like, just download these files. And then we're going to go into Google Colab. So if you just search up like Google Colab, like it will take you to there. Open a Colab notebook, and it should take you to something like this. And we will be hitting going to upload and uploading these questions to open up. So I'll give you like maybe a couple of minutes to like get that set up. And if you need help, please raise your hand. All right, and once you do have this notebook set up, since like, are you guys able to see? Okay, I'm gonna zoom in a little bit. Since we need a GPU, so Google Colab is pretty much like the same thing as the IBM platform that we've been using. It allows you to run a Python notebook and such, but we can go into in this top tabs over here, we can go into runtime. We go into change runtime type. And currently you can see that like we're using a CPU, but we're gonna change to use the T4 GPU instead. Like the specifics of why, like we don't need to know right now, but essentially like now like all our vectorization, it will be on the GPU instead of a CPU. And if you go into research, you know that people are going to be fighting over GPUs. So now we're going to go into files. Just give it a hot second. And we're going to need to upload our utils file as well. So utils.py that we downloaded earlier. So essentially in Colab, like this space is kind of like temporary, this files folder over here, but you're able to upload like CSV files, you're able to upload your own data and pull it from these notebooks if you want to, like say, not grab something from the internet and upload your own information. All right, so essentially what this in this notebook, what we're going to be going through is kind of like different iterations of, I guess, model evaluation and kind of seeing like why is it important to like compare your model to something else or like to compare a model to a baseline. So we're going to be introducing concepts such as like convolutional neural networks and also something called PCA, so principal component analysis, which the details you don't really need to know. I will say if you're going to be taking CSC 311 in the future, you like these like principal component analysis probably will come up. But it's like the details we can gloss over that right now. The main important thing is the like model analysis. So first we're just gonna run. So oh wait, does everybody have it set up already? Okay. Yeah, so first we're just gonna pip install some of our like dependencies and such, just to make sure that they're there, and it looks like most of them are already installed, so that's perfect. And then we're going to just load up some of our like dependencies that we need. Yeah, so the as that is loading, we're going to be using this CFAR 100 dataset, which is a benchmark for image classification. And like as the description says, it contains 60,000 32 by 32 colored images that in 100 classes with 6,000 images per class. So that is a lot of images. We're just gonna load it straight up from Hugging Face, and then first we're gonna compare to grayscale to simplify training on a basic CNN architecture. Yeah, so let's we already loaded it up, so let's or like, we already have the code, so let's load it up and kind of like see our images. Yeah, okay. So like these are just kind of like examples of the data set. So we split it up into 50,000 training images and then 10,000 test images. So that's kind of split. And then so what we have here is kind of like examples of our images. Obviously, like they're not that well grained, but like you can still kind of like be able to tell. Let's say this is a house, a chimpanzee and such. And then these are examples of classes that like are in this data set. And these are going to be the images that we're going to try to train models to predict. So first we're going to go into, look into something called principal component analysis. And then we're going to combine that with, we're going to combine that with a logistic regression classifier. Essentially what principal component analysis does, it's taking, it's going to be just taking the image, it's going to be flattening into a vector, and then it's going to be like try to project it to a lower dimensional space to lower the dimensionality of your data. So the lower the dimensions, basically, essentially, we're kind of stripping it to its eigenvalues and the eigenvectors. And like you don't really need to know the specifics of this algorithm, but it will probably come up in a future like machine learning course if you do decide to take some in the future. So I'm just gonna in this student PCA baseline, we're just gonna get started a little bit, and if you have trouble following along, please let me know. Yeah. So the first things that we're going to be needing to do are going to be, as it says here, flattening the images. Then we're going to be fitting our PCA, training it with logistic regression, and then we're going to need to calculate our compute accuracy. So I'm just going to add up here first, since we need to, from sklearn, we're going to need to import our PCA and logistic regressions. So I can't type. Are you guys able to see this, by the way? Okay, okay. Okay, so yeah, essentially we're loading in our PCA model, and that's going to like help us strip down our images into just the core components. And then we're going to be doing logistic regression on them later. So let's just have that there for now. And first things that we're going to need to be doing, we're going to, in order to do PCA, we need to flatten these images. So let's go ahead and do that. So we're given our train images and also our test images. So let's flatten both. And this reshape is essentially just going to, give me a second. This reshape is essentially just going to, like as it says, reshape these vectors or reshape these images into just into a one-dimensional vector. So like the -1 basically at the end is just saying like fill in the gaps. And you're gonna like if you're going to be doing like machine learning in the future, like this is a common thing that you're going to be seeing. And then let's do the same with our test. Okay, then we're going to do the principal component analysis part. So in principal component analysis, we're going to be having some, we need to make sure that the number of components that like, or the dimensionality like doesn't exceed the number of features that we have. So let's just make sure that we do that real quick. Shoot. So essentially, we're going to define a variable k that's going to be the minimum of our n components. And basically, we're going to be just making sure that the number of components that like we're actually going to be making isn't going to exceed the number of features that we have. So that's what this second half is doing. And then we're going to define our PCA algorithm. And now I'm going to give you guys a, sorry, give me a second. Essentially, the rest of this algorithm that like we need to do is going to be fitting our PCA and then using the logistic regression to predict our or to classify these images. So I guess the next things to do are going to be, I'm just going to write them down, fitting PCA. And then also classifying. And first we're going to be fitting our, give me a second. We're going to be fitting our PCA to to our training set. So essentially, like we have defined our PCA algorithm, and we're going to be, like I said, we're going to be kind of fitting the algorithm to our training data set. And now that it has been fitted, we can run it on our test data set. Yeah, so this part I'm going to be saving for later. This will come into play when we're trying to evaluate our algorithm. But then before that, let's also define our logistic regression classifier. And we're just going to set a max iteration so that, oh wait, it's just max iter of 500. So like it doesn't like run for too long. And to make sure that we have reproducible results, we're just going to set our state to, or like, we're going to seed it to 0. And similarly, we're going to fit to our training PCA. Did I spell that wrong? I spelled it wrong. There we go. Why is it still screaming? Okay, there we go. So now essentially like we fit our PCA algorithm and also our logistic classifier algorithm. And now we're able to our training data set. And now we're going to go back to our testing data set to kind of evaluate how good these models are. So let's go, let's do a prediction now. I'm just gonna do this. So essentially, like this is kind of this similar to what's happening over here. We're taking our transforming our test data set through the principal component analysis to strip it to just its eigenvectors and eigenvalues. And then we're going to be passing it into our classifier to actually classify these images. And we previously have defined in our utils function or our utils folder an accuracy evaluator. So we're going to just straight up use that to see how good our model is. And accuracy is like just as like we explained in the slides. It might not be the best what's it called like metric to use based on your scenario. But in this case, it's good enough to see to evaluate our like these different models in this classification problem. So I'm just going to, why is it, okay. We're going to pass in our test labels and then pass in our predictions. And at the end, we're going to return our accuracy. So once we have that, I'm just going to leave that up there for a little bit. I'll remove this to do comment. And once we have that, let's just, oh, did I forget something? Wait, give me 1 second. Looks like I forgot. Oh, whoops. So in our log class in our classification fitting, I forgot to pass in the train labels. Very important, guys. Please don't do that. As you can tell, I haven't done classical supervision or supervised learning in a while, but if you're going into this field, like you always want to like evaluate your train label somehow. All right, and that should work now. Yeah, so essentially like we already coded up a little bit of things in our utils file to kind of evaluate our model. And we're just kind of running it right now on a smaller data set. So like just to see right here if our model is valid. And then we're going to we already figured out that like our model is valid, and now it's just passing it through our testing. So as you can see, the accuracy isn't that great. It's only around like 15%, which for 100 or for like 100 classes, that might not be terrible. But yeah, I guess like right now, are there like any questions so far? Okay. Yeah, I'll leave this up here for a little bit longer, and then we're going to go into the second part, which is like a more classical convolutional neural network, which you're going to be seeing more for image classification. Yeah. Okay. So this next part is we're just gonna kind of like code up a more simple like convolutional neural network. So how convolutional neural networks work? Essentially, they process images by learning filters to like extract patterns. So let's say if you have an image, if we go back to our images from earlier, like say we might have a network that like detects like straight lines or like vertical lines, and that like might indicate like a house or whatever, because like houses are usually like more bricked or like more boxy in a sense compared to, let's say, a worm. You might also have a convolution, different like CNNs with filters that like might detect like say triangles or like curved edges. Yeah, so we do have a couple of hints over there at the top, but I'm gonna walk you guys through through a model that like you might implement in a sense. If you guys do get lost, please stop me and let me know, and I will explain. So if we look at our hints, we're just going to define like we need to define like a singular like neural network that passes through a convolutional layer, and then we're going to pass it through a ReLU activation function, flatten it, and then do a linear layer for our final classification. And for this one, we will be using PyTorch because PyTorch is a very commonly used machine learning library. And it is like used a lot in research. I used it personally in my research, and it has a lot of like of these layers that are already predefined. So before we get started with actually building the layers, first we need to know how many categories we're actually going to be classifying. So I'm going to define a parameter called n classes, which we'll be using later. And this will just be our, this will kind of be the like total length or the total size of our last output layer. So this is going to be coming into play for our last classification. And secondly, what we need to do, we also need to know how to augment our images in a sense so that it can be fit into our neural network or to our neural network. So I'm just going to define variables for the height and width. So that's going to grab, the reason why we're not using 0 is because 0 is the number of images that we have. And like, this is like the first dimension. So this is going to be our height. And then we're going to grab our width. All right. Just so I like have a sense, like, have you guys used PyTorch before? Okay. If you get lost, please let me know. But essentially, like a lot of times in machine learning, we're going to first like define our model. And then we're going to define the layers of the model, and then we're going to pass that into like our training set. But like we kind of abstract that away by just calling like model.fit or model.train. So following these hints up here, let's let's define our class for the model. And I'm just going to define it in here, and I'm going to call it simple CNN. And it's going to be a child of like, we defined torch earlier, or like we imported torch earlier. So we're going to be using torch.module. I think it's called module. Oh no, I lied. It's capital. So essentially now we have, essentially this is going to be our model that like we pass in our data to, and it's going to output our classification. So as with all Python classes, we first need to define an init function. Yeah, and then now we're going to need to actually build our layers. So essentially how we do this is like, we'll be defining layers like one by one, and then we're going to be having a forward function. We're going to define a forward function that's going to take in these layers bit by bit. So first things first, we're going to define our first convolution layer. So which I'm just going to be calling con. And we're going to be using this right here. So I'm just going to copy that over. And essentially, this is like our first layer of this CNN. And so next, we're going to pass it through a ReLU. It was at, oh, whoops, ReLU activation layer. Next, we're going to flatten it. And finally, we're going to pass it through a linear layer to do our classification. However, like to actually build this linear layer, we kind of need to know the dimensions. So the first one is the first one is going to be in features, which is the dimension of the output of the previous layer. So like essentially what's happening is that as we pass our data through, it's some of these networks or some of these layers are going to be changing the shape of our data, and we need to make sure that like the shape of one passes through correctly, like it matches the input shape of the other. So we're going to be needing to we're just going to do a really quick calculation here to calculate our size of the last layer of this. And like don't worry about the math here because this is just calculating based on like a convolutional layer. But like just the idea of like making sure that you're passing in the correct dimensions, that's like the important part. Because like if you're doing homework, more than half the time you're going to find that like your errors are going to be dimensionality errors. And that's something I ran into a lot. So that's going to be oh whoops, why are you? And then the next one that we need for a linear layer or is going to be the number of outputs, or the dimension of your output layer. So that's going to be our n classes, which we defined earlier. And that is our neural network. So essentially, when we pass in our data, it's going to spit to this model, it's going to spit out a prediction. And that's what the forward function will be doing. So it will take in some piece of like some image that you want to predict and pass it through all these layers and then spit out the final prediction. So that's essentially what the forward function does. So we're just going to take X and pass it through all these different layers. Yeah. Does anybody have any questions so far? Are you guys able to see this? Do I need to zoom in more? Is that okay? Okay. Yeah. Okay. So that is our that's our model that we're going to be training on. Let me just double check. So now that we defined our model, we're going to go back to our data set, and we're just going to make sure that you're able to pass it in through this model, because right now it's currently in NumPy arrays, but to use PyTorch, we need to convert it into PyTorch tensors. So this is just going to be a really quick. So essentially what from what this is doing, it's straight up just converting like data type from a NumPy array to a PyTorch tensor. And just to we're gonna add a dot float at the end just to make sure that these stay as floats and not integers. And we're gonna add a, give me a second. Wait, give me 2 seconds. Yeah, sorry. So essentially, we're making sure that's converted to a float, and this one is just kind of making sure that like checking dimensions and such, like to make sure that we're able to pass it into our neural network. And we're just going to do the same to our train labels as well. Wait, I think, yeah. And we're just going to straight up copy this for our test data set as well. So I'm just going to quickly do that. So now that we defined our training data sets and our testing data sets, making sure that they're going to be able to, you're going to be able to pass them through a PyTorch model. Now we're actually going to get to the model build, like just defining the model and like training the model. And along with the model, we need to also define a loss function. And we also need to define an optimizer to tell the model how to like update itself. So what we're going to be doing is we're just going to first define our model. And it's going to be of the this class. And just to make sure that like we're going to be just to like ensure that we're going to be using the GPU, we're just going to pass it through. Did I? Yeah. We're just going to cast it over to make sure to put it on the GPU. So this is what the .to device is doing. We defined device earlier. Let me just go find it. Yeah, we defined device earlier to be using CUDA, which is which is the GPU if it's available. Otherwise, we're going to be using the CPU. But like earlier, we selected that we're going to be using CUDA, so that will be on the GPU now. And I'm going to define another variable called criterion, which is just another common name for our evaluation metric, our loss. And for this one, we're going to be using cross entropy loss, which is also like defined by PyTorch. Yeah, are you guys familiar with cross entropy loss? I do believe it was covered earlier in the series. Yeah, okay. Yeah, if you need to review it's basically just like checking like how close you are to what's it called? Like the loss and such. how close your prediction is to the actual value of the label. And then we're going to define our optimizer. And for this one, we're going to use SGD. Which one you actually use doesn't really like, it's not going to affect this overall like structure of training and such, but essentially like this is just a common thing that like you're going to keep seeing in a lot of machine learning like making models and such. And we're going to define our learning rate. So the optimizer is going to basically be telling how fast your model should be updating and how it should be updating. So now that we defined that, we're going to be going into our training loop. So we're just going to make sure we're going to set the model to be in a training state. And when you're training a model, you want to like do multiple passes of these. You're going to want to be doing multiple like iterations. So we defined earlier on num epochs is basically going to be the number of iterations that you have. So we're just going to loop over that. I cannot spell. Okay. There we go. And for each of these iterations, we're just first going to reset our optimizer to make sure that it doesn't carry over any information from our previous pass-through. And now, so first we're going to just straight up pass in our training data into the model. So that's going to be our outputs. And you're able to call your model just this way. So this is going to pass in the training tensor or your training data through this forward loop and give you your outputs. And now we're going to evaluate it. So we're going to see the loss. Against our train labels. And based on this, we're going to do a backward step. So this is going to be your back propagation. And we're going to, the optimizer is now going to take a step through to do this optimization. And this is essentially our, what is called a full batch training loop. So this, was full batch and mini batch, was this like covered before? I'm just wondering. Okay, so essentially like what's going on is that like we're straight up testing on all of our training data set all at once. This is something that like is good if you just want to like kind of generalize your data and like take the average. Sometimes though, this isn't exactly, this isn't going to be specific enough, and you're going to see that a little bit later. And it's not able to capture the like kind of the finer details that a model might need. So if you're curious to learn more about like these full batch and mini batches, you can search up like machine learning, full batch, mini batch descent and all that to kind of like see like to kind of see more information about this. And usually it is covered in machine learning classes, but due to time, I will not be going that much further depth into it. So we finished our training loop and now we're just going to do our testing loop as well. So we're going to set it to be in an evaluation state. And just to make sure that we're not updating that we're not doing any gradient updates anymore. We're going to define torch.nograd. So this is like getting rid of all of our gradients, making sure that our model, like just to be sure our model is not going to be updating anymore because we're evaluating it now. And we're going to pass in our test outputs, or we're going to pass in our test set to get our outputs. We're going to grab our predictions. Yeah, so essentially like the test output is going to be like a tensor of these like it's going to have like values for every single like class in a sense, and we're just making sure that it's we're just grabbing the highest class. And we're going to convert it back to a NumPy array to be able to use our accuracy function that we defined for you. And to do that, we need to pass it back onto the CPU. And then similar to before, we're going to use the accuracy function. Okay. Oh, I cannot spell.